Okay, we're going to start talking about um, kinematics or motion now. All right, we kind of got the preliminaries, mathematical preliminaries out of the way in the last few lectures. So we're going to start talking about motion of a particle in this case, and the special instance where we have constant acceleration. And there's some generalities and some shortcuts you can take on when you know that the acceleration is constant. Now, there's some examples of constant acceleration, for instance, motion of the particle like near the Earth's surface. If you're not going very far, you can make some assumptions that the motion of, say, a projectile is under constant acceleration. If you're assuming that, the Earth is flat and gravity is always pointing in the same direction, you're ignoring any sort of uh, um, complexities like the fact that the Earth is moving around the sun and all this other stuff. If the factors are small, you can make the assumption that acceleration winds up being constant. All right, so we can just use these definitions. Let's see where it takes us. All right, so first of all, I'm going to write down the fundamental theorem of calculus in terms in sort of symbols that represent the quantities that we're looking at. So, and it's good to kind of put this into an intuitive framework, So we're engineers and whatnot, so sometimes it's basically we're not too worried about the mathematical rigor sometimes. We just want to know what's going on and how to use mathematics to make it work. Uh, if you're interested in sort of mathematical rigor, you can always look into that. But um, stated in my own terms, what we have here, this is the fundamental theorem of calculus written in terms of velocities and accelerations. So the total change in velocity is equal to the integral of the derivative of velocity. In this case, it's going to be the acceleration. Another way of saying that might be that the total difference in the velocity is equal to the sum. So the integration is just a fancy way of doing a sum of all the tiny changes in the velocity. Okay, so that's the fundamental theorem of calculus. And uh, so because in our special circumstance we're dealing with constant acceleration, the acceleration can come out of the integration. And so that is just equal to that. All right. And so T naught is just the initial time of consideration. And we can set it to an arbitrary value, so we can always set this to 0. Really, so what we're saying here is the duration, right? So the difference in velocity between the two endpoints of the duration is equal to the constant acceleration, in this case, times the duration itself. All right, so we're going to set t0 equal to 0 and introduce a shorthand so that the velocity at time t0 is just going to be v0 or v naught. I may say v naught sometimes, but rewritten with this notation in mind, we can say that the velocity at time t is simply equal to the initial velocity plus this constant acceleration times time. All right, so there's a simple consequence of our assumption of constant acceleration. All right, and then likewise we can repeat that for the position. However, the velocity is not constant, so we'll substitute in our formula for the velocity. So that's just and skipping a couple steps here, but you'll be able to, I mean, you guys could pretty simply go from here to here. I'll leave that as an exercise, I guess. Okay, you know, with still the assumption that T naught is equal to 0 and V of T naught, or yeah, is equal to V naught. So V naught is just the velocity at time equals 0, so on and so forth. So getting from here to here, I'll leave that up to you guys. It's pretty simple. But if you have any questions, feel free to ask. All right, so I can rearrange this. Where R naught, you know, just to be all right. So sometimes you would like to eliminate time from the equation. So say an example that's going to come up here in a second. We're going to get into this, but say you would like to know how far a projectile you're more interested in the path. You'd like a parameterization in terms of the path, and you're not really interested in time, for instance. So, you know, so you might be able to do something like, given I think you might be able to, like, given some projectile motion, you would like to be able to illustrate the path and see how far it goes. So you've eliminated time from the equation. All right. You don't really care when the projectile strikes the ground, but you'd like to know where it strikes the ground. So that's just a quick example of when you might want to eliminate time from the equation. So to do that, first thing we're going to do is solve for time. Now, doing that in vector form with this sort of notation, I think it's going to wind up being counterproductive. So what I want to do is go ahead and expand these two things in front in terms of Cartesian coordinates. So starting with, we'll call this equation 1, and this equation 2 maybe. So starting with equation 1 and expanding that in Cartesian coordinates, we have so this is a t, the time coordinate. Okay, so that's just this equation expanded out in terms of ij and k. And now what we have here are 3 independent equations in terms of ij and k. All right, so in terms of I, so And then again, in terms of j, we have the y coordinates. And then in terms of k, we have the z coordinates. All right, and so I can use this to solve for time. And so I solve this equation for time and this and this. And so you get three different definitions of time in terms of the x, y, and z coordinates. So the time, you know, and then I can take this definition of time, plug it into this, and I can eliminate time from the equation altogether. All right, and so I'm only going to do this for the x coordinate, and then it's pretty simple to verify this for the y. It's the exact same procedure, but we can do the same thing for the y and z coordinates. So first, I'm going to take r naught and move it to the other side. So in okay, and it's substituting so obviously the more productive substitution will be in terms of the x coordinates. So okay, now I'm going to multiply through by 2 times the acceleration. I mean, I'm doing this because I know, because I've spent, you know, a little bit of time figuring out what needed to be done. Okay, so it's not for me, it wasn't immediately obvious as that's how you need to solve this equation. But once I did solve it, this is you know, you make the realization that sometimes that's how progress is made. So multiply both sides by 2 times the acceleration with respect to x. So what I get over here, so 2 times the acceleration, the half cancels, and I get acceleration squared, and that cancels with this acceleration squared, so I'm just left with the difference in velocities squared. And so I can expand those to the right hand side. And so we have some immediate cancellations. This cancels with this. I have 2 v naught x squareds here in the negative and 1 positive. So And so I can rearrange this so that sort of the final velocity, if you want to call it that, in the x direction is equal to the initial velocity. Well, no, so I'm sorry, these two quantities are squared, plus 2 times the acceleration times the displacement in the x. Okay, so if you want to know the distance traveled, you know, maybe you can. Bottom line is, this is another parameterization with the time eliminated, and there's probably a lot of examples as to why this would come up. I just can't think of any right now besides the projectile motion that we're going to get into in a little bit. Okay. So likewise, for this equation is also true for y and z. So you know, just for completeness sake, I guess. All right. So sort of the typical case of constant acceleration is exactly this: the motion of projectile, where we have essentially a 2D path traced out by an object that is fired or and has an initial velocity, has an initial position and initial velocity governed by whatever parameters you'd like. So a lot of times what you'd have is, say, you would be given the magnitude of the velocity, okay, and perhaps a typical case would be you're given the magnitude of the velocity at time 0 and the angle at which it's fired at time 0. All right. So in that case, it's just pretty simple that v naught x is just equal to the magnitude times cosine, and then v naught y is okay. Now you can actually explain this in terms, just for completeness sake, I'm going to go ahead and write this down, but v naught x is just in terms of the vectors, oops, it's just a projection of the velocity vector onto I, right? This is the unit vector in the direction of x, and likewise, this is just for completeness. I want to try to get you guys thinking in terms of vectors. I find that it's a lot more intuitive. Maybe you don't. You guys, maybe you will always settle back into dealing with sines and cosines and stuff like that. But I find that when dealing with this sort of notation, the formulas become a lot more intuitive, a lot more geometric. You know what I mean, and kind of easier to understand. So all we want is the projection of the velocity, of the initial velocity, onto the the unit vector that's pointing in the direction of the x coordinate, and that's what gives us v naught of x. That's true for any vector. All right, and so now we just use the formulas that we have available to us. So, like, this is going to be kind of repetitive, but so we can just use, if we want to know if we want to know certain quantities about this trajectory, we can just use those equations that we just wrote down. So, so Vx is equal to V naught x plus AC x times time. What is AC of x? In this arrangement, because gravity is pointing directly down, it's just the acceleration due to gravity, and it's pointing directly down in the y direction. So the acceleration with respect to x is 0. So the velocity of x is equal, at all points along the trajectory, is equal to the initial velocity of x. So it never changes. All right. And likewise, the position component of x again, AC of x is 0, so this just simplifies to all right, so it's just a linear relationship with velocity. Now, the y is slightly more complicated because it's non-zero, but and so um, substituting the y component of acceleration in just gives us that. All right, and then so the position with respect to y and now like the eliminating the t variable is really only productive in the y direction, because you just wind up getting, in the x direction you just get vx squared equals v naught squared. So in the y direction, so